Okay, the TD lambda action value variant is known as SARSA lambda for learning Q values. So we keep in SARSA lambda, we keep an eligibility vector over all of our tunable parameters in the function approximator. We of course update the eligibility at each time step and decay previous eligibilities. We compute the small delta, the TD error, and update our tunable parameters based on their eligibility and the delta and the TD error. So this is the pseudocode for online SARSA with linear approximator. By the way, why is this only applicable for a linear approximator? Do you know? Any idea? There's a clue here. So you can see that in this pseudocode, the gradients of the tunable parameters of the function approximator with respect to the tunable parameter is simply x. And this is the case for a linear approximator, right? We saw that before, but of course we can extend this to other types of approximators. We'll just have to take care of or set up the correct gradients. For instance, a deep neural network with a backprop algorithm. Okay, so moving forward, can we do Q-learning or off-policy? So SARSA, of course, is an on-policy algorithm. And in many cases, we would like to apply an off-policy algorithm, such as Q-learning. Right? Q-learning, one step, we don't commit to the next action, but you take you choose the action with the maximal Q value in the next state. This is how you perform development updates. Usually we try to learn Q star, which is initially unknown, and we try to converge on it, which also, once we learn Q star, of course, it implies pi star, the optimal policy. Now, in order to avoid convergence to a local optimum, as before, the Q-learning and Q-learning approach must explore sufficiently, right? We have to do infinite often visitations. So, for instance, by using an epsilon greedy approach, we can have this property. However, eligibility traces assume that the underlying trajectory is sampled from the evaluated policy, right? So eligibility traces, similarly to n-step return, is an on-policy approach. So then it raises the question of how should we update eligibilities for Q-learning once a non-greedy action is taken, once we do attempt to do off-policy learning. And so there are several options here. Some of them are pretty simple, some of them are a bit more complex, but I would say the most straightforward approach would be to simply zero out the eligibility after a non-greedy action is taken. So once you detect that you are off policy, right, we take an action that is not based on our current maximizing Q values policy, we take a random action, we simply set all of the eligibilities to be zero. Okay, we zero out all of the eligibilities, else we accumulate them as normal. So a straightforward solution here would just be to zero out the eligibilities once we diverge from the greedy policy, from being on policy. So once we become off policy, we simply set all of the eligibilities to zero, right? So this is exactly what we do in Watkins's Q Lambda learning. This is the naive variant. So as before, once we encounter a specific state and action pair, this is for a tabular setting. It can be extended also for an approximator setting. But once we visit a specific state and action pair, we set its eligibility as before. And for all of the other state and action pairs, if we're doing we are doing Q learning, right? So it's for state and action pairs, the eligibilities. For all of the other state and action pairs, we decay the eligibility. However, if we diverge from the current greedy policy based on our current Q values, we simply zero out the eligibilities. Okay? So that's a straightforward way to implement Q Lambda. So this is the pseudocode for Watkins's Q Lambda. As I said, this pseudocode is for the tabular version, but it can be easily extended, as we've seen before, for the approximation case. Next, we have Peng's Q lambda. So this is a bit of a more advanced version. It tries to address the disadvantages of Watkins's method, where the eligibility trace will be cut or zeroed out frequently. Each time we take a random action, it will be zeroed out. And this might be not sample efficient, right? It might result in little advantage to the traces. And so Peng said that he suggested to back up the max action except at the end of the end step trajectory. It never cuts traces. The disadvantage is that it's a bit more complicated to implement, and the results don't always justify this complication. And I'll show you some results in a second. Finally, we have a naive approach that never zero out traces. Even if we are off policy, we still won't zero out the traces, and we'll always back up values at the current action. Right? Even if a non-greedy action was chosen. Okay, so let's compare the three approaches. So I'll show you some results comparing Watkins, Peng's, and the naive. The naive approach in the textbooks is also called the McGovern's, also in the results that I'll show you in a second. The results are for a deterministic grid world with obstacles 10 by 10 in size. There are 25 randomly generated obstacles, and the results are averaged over 30 runs. So we'll show you the results after 30 runs. Learning rate is set to 0.05, gamma is 0.9, lambda is 0.9, and epsilon for epsilon greedy is 0.05. And we're accumulating traces. We'll see a different approach in a second. Accumulating traces just means that each time we visit a state and action pair, we'll add the addition that we defined to the current eligibility. Okay, so we don't zero out and set it to the initial value, but we always add these values together. I'll show you an example of this meaning, and we'll discuss accumulating traces in a second. Okay, so these are the some of the results, the training curves. On the x-axis you see the number of episodes for each training, and on the y-axis are the how many steps were needed in order to get to the goal. And of course, lower value is better. Lower value implies a better policy. And in these results, you can see that it seems like the McGovern approach, which is just the naive one, we never zero out the traces, seems to work best because it kind of makes sense. It's most sample efficient, although the updates might be a bit off. They are off policy, right? To some extent. But it's still the advantages of the sample efficiency outweigh I would say, the correctness of implementation, right? When we actually zero out the eligibility. And you can see that Watkins is a bit better initially, a bit slower later on compared to Peng's approach. Yeah, so there's no clear winner between Peng's and Watkins, but it seems like the most naive approach, the McGovern approach, works best, at least in this domain. What about convergence guarantees? So none of these methods are proven to converge. None of the Q lambda methods that we just discussed is guaranteed to converge. Watkins says is thought to converge to Q star. Peng says is thought to converge to a mixture of Q pi and Q star, right? Where Q pi is the noisy exploration, the epsilon greedy exploration, for instance, or whatever exploration technique that you're using. Okay, going to the question regarding accumulating traces, and I'll discuss it now. So another option would be what's called replacing traces. So let's define that. So I'll define it now. So in replacing traces, it means that each time we visit a state and action pair, we reset its value to the initial value, and we don't add the values. Okay, we don't add. So it can't be that over time some eligibility will grow to be larger than 1 for a specific state and action pair. If we use accumulating traces on the other hand, then frequently visited state action pairs, if we're doing Q learning, can actually end up having eligibility that is greater than 1 because we accumulate these eligibilities. And this might be a problem for convergence in many cases, right? And replacing traces is where instead of adding one or the initialized value, as I told you before, we can replace it with 1. In some cases we do. So instead of adding 1 when you visit a state, or that specific value that we discussed previously, we reset the trace to be 1. Okay, so on the right here you can see how if a state is visited several times with accumulating traces, we might reach eligibility that is greater than 1. With replacing traces, we can resolve this issue. And in fact, when we examine in many domains, replacing traces is beneficial. It performs better than accumulating traces over more values of a lambda. Right, where lambda is our trajectory consideration, or how quickly we decay our eligibility. That's a hyperparameter. And indeed, you can see that in 2 domains, in the mountain car domain, we can see a clear advantage for replacing traces over various lambdas, maybe not 0, but for all of the other lambdas, we do see a clear advantage for replacing traces, while in the random walk domain, we still see advantage for replacing traces. However, it's lesser, I would say, than accumulating traces. But in any case, at least in these 2 domains, accumulating traces is never beneficial over replacing traces. And what's the intuition here? So let's look at a toy domain to try to demonstrate the issue with accumulating traces. What will happen in the following domain if accumulated traces is used? Okay, so here in each state we can either take the right action or the wrong action. Okay, if we take the wrong action, we simply stay in the same state. And if we take the right action sufficient number of times, we'll get some positive reward. Once we'll get this positive reward, then we'll go back and look at our eligibilities to learn from this reward, right? Some of these state action pairs will have higher eligibility, that is, the positive reward will impact them stronger, it will give them a stronger signal that they should be visited or taken more often, these actions. Which actions here will have a higher eligibility?
The wrong action.
So the wrong action if you repeat them, right? So in some sense, I can repeat the wrong action in this, you know what, let's say in this state here, at the state at the end. If we take the wrong action several times at the last state there, the eligibility, if we accumulate it, will be very high for taking the wrong action at state S. Eventually we'll take the right action and we'll decay all of our previously accumulated eligibility, but we'll just decay it a little bit and it will be accumulated to such high value that it might be higher than the eligibility trace for the right action. So in some sense, this can really skew my learning towards frequently visited state and action pairs, even if they are the wrong action. Okay? So this is just an illustration of what can go wrong.